Section 3.5, Implicit Differentiation. Implicit differentiation is the method of differentiation of both sides of an equation with respect to x, and then solving the equation for y prime when y equals f of x. So sometimes we have equations that are not functions, so it doesn't really make sense to try and find a derivative of something that's not a function because we don't have y equals something. So we can't just write a derivative using any of our previous methods. However, we might still want to find the tangent line to a curve that's not a function. For example, a circle. Like if x squared plus y squared is 25 in this example, we would love to be able to find what dy dx is. So in that case, we kind of cheat a little bit. We take the derivative of everything, pretending that it's all with respect to x. So we leave any derivatives of things that are not with respect to x, or not directly, as just their own derivatives using the chain rule. And then later on, we solve for those derivatives. So what this means is we're going to take the derivative of x squared, which we know is just 2x. And when we take the derivative of y squared, we'll pretend that it's like x squared, so it'll just be 2y. But we'll have to use the chain rule because it's actually a function of x, and we'll have to multiply by the derivative of that function of x. So let's do this. dx, the derivative of x squared plus y squared is equal to the derivative of 25. We're taking the derivative of both sides. So that means that this is the derivative of x squared plus the derivative of y squared, and then derivative of 25 is just 0. So then derivative of x squared, derivative of y squared. Now remember, this is, we're going to treat this as its own variable. Y is a function of x. It's kind of like when we had f of g of x. You wanted to take the derivative, you would do f prime of g of x times g prime of x. So in this case, if we want to get this derivative, f of g of x prime, we want to get the entire derivative, that's this thing over here, then first we have to take the derivative with respect to g of x, and then take the derivative of that g of x. So let's take the derivative of this thing with respect to y, and then multiply by the derivative with respect to x. So derivative of x squared is just 2x. Derivative of y squared with respect to y, we're treating it like as if it was just an x, is just 2y. And then we keep our dy dx from the chain rule. So then we can move the 2x to the other side by subtracting. We get 2y dy dx is equal to minus 2x. So that means that dy dx can be solved for by dividing both sides by 2y. So negative 2 divided by 2 cancels, so you get negative x over y for the derivative. So it's not as straightforward. You have to actually solve for what your derivative would be instead of just differentiating and then just ending up with it. Let's find an equation of the tangent line to this circle now. Well, we just saw that the derivative was negative x over y, and we want the derivative at the point 3, 4, so we'll just plug in 3 and 4. We get that the derivative must be negative 3 over 4. Okay, so we want an equation of a tangent line, so y minus our y value is equal to the slope, which is the derivative, negative 3/4, and x minus our x value. That gives us point slope form for the line. So then we can, if we want, we can put this in standard form as 3x plus 4y equals 25. And that's the equation of a tangent to the circle at the point 3, 4. Let's find y prime if x cubed plus y cubed is 6xy. So we will differentiate both sides. When we differentiate the left side, we get 3x squared for the x one. That's easy. If we're differentiating y cubed, we're going to pretend it's as if it was x, so that's 3y squared. However, it was a function of x, so we have to multiply it by its derivative, y prime. So that's equal to 6x y prime plus 6y, because we have to actually use the product rule here. 6x is a function of x, y is a function of x, so that means it's 6x times the derivative of the second guy, and then it's the derivative of 6x, which is 6, times the y without the derivative. Okay, so we can divide everything by 3 and get that this is x squared plus y squared y prime is equal to 2x y prime plus 2y. So now we want to try to move all of the y primes to one side so we can solve for y prime, which is the derivative. So how about we move them all to the left? We get y squared times y prime minus 2x y prime is equal to 2y minus x squared. We subtract x squared and we subtract 2xy prime. So now we can factor out the y prime because it's in this term and this term. So we end up with y squared minus 2x times y prime is equal to 2y minus x squared. We divide both sides by y squared minus 2x, and that gives us y prime all by itself. So for every single one of these problems, you have to differentiate and then isolate your derivative by moving everything over to like a single side. Let's find the tangent to the folium of Descartes, x cubed plus y cubed equals 6xy at the point 3, 3. So that's actually the name of this fancy thing. It looks something like this. Didn't come out good. Let's try it again. A little bit better. It's supposed to be at 0 over there. Okay, so we want the point 3, 3. We're looking for the tangent line. So we'll return to this in a minute. Y prime, by what we just calculated, is equal to 2y minus x squared over y squared minus 2x. We can plug in 3, 3, so we get 2 times 3 minus 3 squared over 3 squared minus 2 times 3. Well, that simplifies to negative 1. So the slope of the tangent line is negative 1. So now it's y minus the y value is the slope negative 1 times x minus the x value. So that becomes x plus y equals 6. Which makes sense because this tangent line definitely has a slope of negative 1 and it's going through and hitting the intercepts at 6. Okay, so now we want the point in the first quadrant when the tangent line is horizontal. So we want to know when the derivative is 0, because horizontal tangent lines have 0 slope. Well, if the derivative is 0, that means that the numerator, this guy, must be 0 when the denominator is not 0. So that means that 2y minus x squared must be 0. We could solve for y and see that in that case y is equal to half x squared. So we can now plug that into the equation for the folium of Descartes. That was x cubed plus y cubed, but we now know that y is half x squared, so that's half x squared and cubed. And then that equals 6xy, so it's 6x times half x squared. We can solve for x. We get x to the 6 equals 16x cubed. So that means x cubed is equal to 16. We can divide because x is not 0 in the first quadrant. Then we're taking the cube root. So we get x is equal to 16 to the 1/3, which is the same as 2 to the 4/3. And now we have an x value. We know that y is equal to half x squared. So we square that, multiply it by a half, and we get that y is equal to half of 2 to the 8/3, which is equal to 2 to the 5/3. So that means that our point is x 2 to the 4/3 and y 2 to the 5/3. If you were to use a calculator, you could see that this is roughly this messy decimal. 3.1748 for the y value. So 2.5, 3, so it's a little bit before this. It's like right around there, somewhere around there. Let's find y prime if sine of x plus y is y squared cosine x. So we'll differentiate both sides. We get the derivative of sine is cosine. But it wasn't just sine, it was sine of x plus y, so we have to multiply by the derivative of that function by the chain rule. So derivative of x is 1, derivative of y is y prime. Okay, and on the other side we have y squared times minus sine x, because now we have to use the product rule, plus cosine, well, the derivative times derivative of y squared, which is 2y, and then multiplying by y prime using the chain rule. So then this becomes cosine of x plus y plus y squared sine x is equal to 2y cosine x times y prime minus cosine of x plus y times y prime, because we want to get all of the y primes to one side. So then we just divide. We get that y prime must be equal to y squared sine x plus cosine of x plus y divided by 2y cosine x minus cosine of x plus y. So you see, whenever you have these guys on the same side like this, you can just factor them out. So you get this mess, and then you just divide by it. Okay, let's find y double prime if x to the 4th plus y to the 4th is 16, which is basically like a kind of, I don't know, fat looking circle. I didn't draw it very well, so I'm gonna forget about that. This is 4x cubed plus 4y cubed times y prime equals 0, because derivative of x to the 4th is 4x cubed. Derivative of y to the 4th is 4y cubed. By the chain rule, we have to multiply by y prime. And then derivative of 16 is 0 because it's a constant. If we solve for y prime, we get that y prime is negative x cubed over y cubed. So that gives us y prime, but we needed y double prime. So we need the derivative of this guy. So unfortunately, now we have to use the quotient rule. So this is the derivative of the derivative, which is equal to, by the quotient rule, minus y cubed times the derivative of x cubed minus x cubed times the derivative of y cubed all over y cubed squared. So then that becomes minus y cubed times 3x squared minus x cubed times 3y squared times y prime. And then y cubed squared is y to the 6. So now that's negative 3x squared y cubed minus 3x cubed y squared times y prime. We can't have y prime in the end though. We need our second derivative in terms of just x and y. So, but it looks like we know what y prime is, luckily, so we can replace that. So y prime becomes minus x cubed over y cubed. And we still have our y to the 6 in the bottom. Okay, that simplifies out a little bit. We end up with 3 times x squared y to the 4th, because x cubed in this case multiplies there to get x to the 6, so we have plus x to the 6, but then this thing multiplies, we get y to the minus 1, we can move that to the denominator, and we can end up with y to the 7th. And notice I also factored out 3. Okay, so almost done. This becomes minus 3x squared y to the 4th plus x to the 4th, because we can factor out an x squared. Now you might be thinking, okay, why would I want to factor out x squared? Well, notice now we have left inside here is y to the 4th x to the 4th, which is exactly what we started with, and we know that that equals 16. So now we can replace that with 16. Okay, so 3 times 16 is 48. So we have minus 48x squared over y to the 7th as our second derivative, y double prime. The derivative of the arcsine function, derivative of sine inverse, is 1 over the square root of 1 minus x squared. So remember that if y equals sine inverse, that's the same thing as saying that sine of y is equal to x. Okay, so because y is between minus pi over 2 to pi over 2, we know that cosine y is greater than or equal to 0. So we have sine of y is equal to x. We take the derivative of both sides. We get cosine y dy dx is equal to 1. We divide by cosine y. We get dy dx is 1 over cosine y. So then cosine y is the square root of 1 minus sine squared, because cosine squared y plus sine squared y is equal to 1. So we subtract sine squared, we take the square root, and it was positive to begin with, so we don't have a problem. But then we said that sine y is equal to x. So sine squared is x squared. So that's just 1 over square root of 1 minus x squared. We can also take the derivative of the arctangent function and see that that will be 1 over 1 plus x squared. Same method pretty much. If y is tangent inverse of x, then tangent of y is equal to x. Derivative of tangent is secant squared. Since it's of y, we multiply by dy dx by the chain rule. Then we divide by secant squared. Remember that 1 plus tangent squared is equal to secant squared. So that means that we get 1 over 1 plus tangent squared, but then we said tangent of y is x, so that's 1 over 1 plus x squared. We can also differentiate to get that derivative of cosine inverse is the same as sine inverse, except that it's minus 1 over square root of 1 minus x squared. All of the co-functions have minus derivatives in general, but the proof is pretty much the same, so you can do that yourself. Let's differentiate 1 over sine inverse. Well then, dy dx is the derivative of sine inverse of x to the minus 1. That's what 1 divided by something means. So the minus 1 hops out in front, becomes minus sine inverse of x to the minus 2. We reduce the power by 1 and multiply by the derivative of what was inside, which is sine inverse of x. So that becomes minus 1 over sine inverse of x squared times square root of 1 minus x squared. Let's differentiate x times arctangent of x. Well, now it looks like we have to use a product rule. So f prime of x is just x, that's our first function, times derivative of arctangent of square root of x, so that's 1 over 1 plus, instead of x, it's square root of x, so square root of x squared. But then it wasn't arctangent of x, it was arctangent of square root, so we have to use the chain rule and multiply by the derivative of square root of x, which is half x to the minus 1 over 2. For the second half of the product rule, we take the derivative of x, we get 1, so we just keep arctangent of square root of x. Okay, so then we can put, we've got a square root of x squared, so that's just x. X will cancel, so we just have x and the x to the minus half, so we just end up with x to the half is square root of x, and then 2 times 1 plus x. That's where half comes in. The square root got squared, become x, and we keep our arctangent. So in summation, the derivatives of the inverse trig functions are listed here. Notice all the co-functions have negatives, as usual. Okay, lastly, suppose f is a one-to-one differentiable function, and its inverse function f inverse is also differentiable. Then f inverse has derivative f inverse prime is 1 over f prime of f inverse, provided the denominator is not 0. So if f inverse of x, if we're looking for the derivative of f inverse, then we know that if we compose a function with its inverse, it returns you right back to where you start at x. So we start with this identity, then we take the derivative of both sides. The derivative of the left is just the derivative of f inverse, the derivative of the right of x is just 1. So now we have to use the chain rule. The derivative of f inverse is f prime of f inverse. However, we then have to take the derivative of what was inside, which is derivative of f inverse, but this is exactly what we wanted. So let's isolate that. We divide both sides by 1 over f prime of f inverse. And then that's our formula. So as an example, we want to find the derivative of f inverse at 5. So f inverse prime of 5 is equal to 1 over f prime of f inverse of 5. By our formula, we're just plugging in 5. So f inverse of 5 is the x value that gives us a y value of 5. Here's the y value of 5, that x value is 4. So we have 1 over f prime of 4, which is equal to 1 over, so good thing they gave us f prime of 4, 2/3. So that's just 3 over 2.